It's my pleasure really to introduce the final speaker today. Is my colleague from Databricks, Burak. Burak has been actually working with Spark since the early release of 1.1, and he also maintains all the Spark packages. So those of you who are actually interested to find out if something doesn't exist in Apache Spark, does it actually exist in Spark packages? So he's one of the maintainers of that. And more recently, he has been furiously contributing to Apache Spark 2.2, in particular structured streaming. And as you know, structured streaming has actually made quite inroads in 2.0 and 2.2. And today he's going to tell us all about arbitrary, stateful aggregation structured streaming, in particular about how to use two streaming joins from Kafka and how to use flat map aggregations. So those of you who actually use 1.6, you know that particular function is quite useful. So give a big hand to Burak.
All right. Hello, everyone. Thank you so much for having us coming. So today I'd like to talk about stateful aggregations that we have in Spark and Spark 2.2. So this is Spark 2.2 is in voting stage right now. There are release candidates out, but I just wanted to show you how cool this stuff is. So hopefully you'll like it. So very quickly, who am I? I'm a software engineer at Databricks. I've become a committer in like February 2017. I did my master's at Stanford, so I was very happy to have pizza on my heart for dinner. And I did mechanical engineering for undergrad, so not really a CS person, but like Spark's great, so great. So today, how I want to structure my talk, basically I'll just give you an introduction on like structured streaming and some of the concepts that will, like outline how we do stateful processing in structured streaming. And then once I show you some examples of, like how, like you do group bys, aggregates, and all that stuff, and how all that works in a fault-tolerant manner in streaming, I'll talk about a couple use cases, and then I'll show you some demos in Databricks on how to connect to like Kafka and like do all this crazy stuff. All right, so let's get started. Structured streaming. Spark has had like a streaming library since its inception. It had like Spark streaming. It had its dstreams API, and what we noticed like throughout developing like Spark was that we've noticed that like handling streaming data is hard. And we wanted to make it simpler, and we thought about like how can we make it simpler? Well, basically we said like the easiest way to reason about streaming data is not having to reason about streaming at all. So once we introduced data frames in Spark 1.3, people had this idea of tables. It has a schema. It has columns. Columns have data types. I get super fast performance because Spark understands, like my data types now. I said, let's just expand this. Like static data frames, they're great. How about if you had infinite data frames? So continuous data frames. Like have a single API, and some things could be streaming. They can be updating over time. Some things you just read it once, use it once, and throw it away. So in our new model, we have three concepts. Basically, you have your input source. So this input source is data from like an append-only table. This could be a list of files on S3, on HDFS. It could be Kafka. It could be Amazon Kinesis. It could be a JDBC like database that keeps getting new IDs appended to it. So basically, you have a data source as your input. Then we have this concept of triggers. These triggers are basically how frequently you want to emit new data. So if you want to emit new data, first you got to check if there's new data. If there is new data, you do your processing, and then you output it. And then you have your query, which is basically any data frame query that you write or SQL query that you write. It's basically operations on the input, like maps, filters, reduce operations, windowing, group bys, aggregation, sessionization, all that stuff. So once we have our trigger, in this example, let's say it runs every second, we have our input data. You can see here it's like in our first trigger there's like data up to 1, we run our query, and then we get a result. So this result, what we output is, we evaluate this query on the input data and we output something. How can we output this data? There are output modes on how we emit the results to you. So the easiest one to reason about is complete mode, which means we run your query as data comes in, and we just give you the full results over time. So this is like if you were to run your batch query. If you were to run a batch query at time t1, it would give you the result in t1. If you were to write a batch query at t2, it would give you the result at t2. So this is basically guarantees you the same answers as batch mode. So we output all the rows in the result table. If you have append output, basically we have new input data coming in, and we only output the new rows that should be added to the result table. So this is basically, you can imagine this as like an ETL use case where you get new data, you process this data, you clean it, and then you write it out somewhere. And one thing to note is that not all output modes are feasible with all queries. For example, if you wanted to do an ETL, we cannot output the complete result every single time. That would be just too expensive. We have to save all the state in memory or wherever, so it's just not feasible. So let me just dive into the output modes a little bit more, because what I'm going to talk about later in flatMapGroupsWithState, we also need to provide output modes for functions. So, like I said, append mode, new rows added to the result table, gets output to the sink. This is the default mode when you write a structured streaming query. If you write stream, format Parquet, and then start, it's by default output mode, append mode. The thing here is that since rows will be output only once, they cannot be rescinded, which means once you output this result here, we cannot change it ever again. And this will basically saying that the output mode is append says that your result is complete, it's true, and it can't change ever again. For complete mode, like I said, it outputs the whole result table. And this is mostly used in aggregation queries, because once you have an aggregation, you have some finite, hopefully some finite amount of state in your query, and then you can output this all at once. So where you would use complete mode is you would use it in monitoring. You could generate dashboards out of complete mode structured streaming queries. And then in Spark 2.1.1 we added update mode, where only the results in only the rows in the result table that changed will be outputted to the sink. So this is kind of like append mode, but here we can change our answers. So we will, for a given key, for example, we will output new values as the new rows get processed. So you could use this for alerting or sessionization. It's mostly used for aggregations. So let's talk about stateful processing. All right, so one thing that a lot of people talked about with D-streams complained about was that there was no real support for event time. It was very hard to actually perform aggregations or perform some operations given the event time of your input data. So with structured streaming, we wanted to make the handling event time as simple as possible. So many use cases in real-world applications require statistics by event time. You want to know how many errors are in each system in 1 hour windows, for example. But there are many challenges to handling event time aggregations. Basically, you have data coming in late, data coming in out of order. Wi-Fi goes out, so once a user gets access back to Wi-Fi, it takes it's like 10 minutes late now. So you need to be able to update and deal with late data. So how do we handle event time aggregations? Basically, windowing is just another UDF in Spark. So it's another like group by expression that you would write in structured streaming. So it's basically you would have a timestamp column, you would window it by, for example, 1 hour. This does a 1 hour tumbling window, and then you could aggregate your values on top of this. If you wanted to, like calculate something like average signal of each device of your like sensors every 10 minutes, you could also group by device in addition to the windows, and then it all works as expected. And the beauty here is the timestamp is already inside your data. You don't need to write any special extractors to use this kind of stuff. It's already like built-in expressions that help you deal with this very easily. Repeating the question, is the timestamp generated by the query, or is it coming from the source? So you could do both, actually. It could be coming from your source, it could be part of your data, and then like once you've parsed it, like it's any column in your data. Or Spark also has like current timestamp method, which could provide you the processing time data to do all these windowing functions. So more advanced aggregations, Spark has a lot of built-in functions for all these aggregations, all kinds of mathematical functions that you love, such as variance, standard deviations, kurtosis. And the beauty of it is you can also, once you window it, you can have multiple aggregations on this very efficiently. So you could, like once you do this grouping, you can easily calculate the average, standard deviation, the maximum, the minimum, 99th percentile, all in a single expression, and it'll all be very efficiently computed for you. It won't generate like 5 different queries for you. And you can do more custom stuff by using UDAFs, user-defined aggregate functions. The dataset APIs also has functions called map groups, which you can map basically groups of data and like output results for it. So for stateful processing aggregations, this basically means that you have to save some state across executions, incremental executions of your query. So how do we do this? So we keep an in-memory streaming state maintained for these aggregations. Once we have this in-memory state, it allows us to, like once late data comes in, we can just update the existing state and update the counts of old windows. And this is how we handle late data. But one thing to keep in mind is if we're gonna keep all the memory in state, and if we're gonna handle late data, what if like we can't keep all the data in there forever, or like our state will grow unboundedly. So how do we handle that? So as you can see, I highlighted one part in purple, one part in orange. These are the next 2 slides. In-memory streaming state. If your state is in memory, how are you fault tolerant, right? But if your machine dies, don't you lose that state? Well, we basically keep a write-ahead log that's checkpointed synchronously to some durable storage. It could be S3, it could be HDFS, it could be Azure Blob Store, it could be anywhere you like. And we checkpoint this state after each trigger, so that once we know what's the input data, what was the state before, we can always replay a trigger, a specific trigger, and get the exact same results. And basically through this structure, you get fault tolerant and exactly once semantics in structure streaming. So how do we make sure that our state doesn't grow unboundedly, infinitely, and like our applications don't crash? So we handle this through a concept called watermarks. So watermarks basically is a moving threshold that moves behind the max seen event time in your data, and or it could be processing time if you want, but totally up to you. Basically, this allows to give some what do you call it? Some time for like late data to come in until you make sure that your result cannot change anymore, and then you can output it. So here in this image, you can see we have event time on the y-axis. We have a the max event time we've seen in our system is 12:30 p.m. We said like we'll have this watermark have a delay of 10 minutes. So we've set the watermark at 12:20 p.m. We don't expect any data to come later than 10 minutes. So this is what we expect as the data engineer, and we set it so. So data newer than the watermark, they can be late, but we will allow it to be aggregated, so you get updated results. Data older than the watermark is too late and dropped. So this way, once we output that, like result, since it's past the watermark, the late data that comes in that's even older, even later, we just drop it. So state older than the watermark is then automatically deleted to keep like the state bounded in your system. So to control the trade-off between like state size and lateness or latency, if you want to handle more late data, you need to keep more state. But if you want to reduce your state, you need to handle less lateness. So there's this trade-off there. And the way you specify a watermark is by this with watermark function. You give it the column of a timestamp column. It could be, again, event time or processing time. And then you specify how much of a slack time you want to give it. For example, 10 minutes here. So as a step-by-step example, let's say we get 3 points, 12:07, 12:08, 12:14. Like our max observed event time is tracked by the blue line. And after the end of the trigger at 12:14, we say this is the max event time we've seen. Then by a slack time of 10 minutes, we set the watermark to be 12:04. So once we get new data, we get like 12:15 and 12:18. We could get late data, for example, like 12:13 and 12:08. Those will still be included in your aggregations. But a point that comes which had an event time of 12:04, that'll be dropped. You can read more about it in this blog post. I believe we'll send out the slides on the meetup page, so you can click the links there. All right. So, example again. Let's do a word count. Very simple. Our input stream has like cat, dog, dog, dog coming in. After like 5-minute triggers and 5-minute sliding window intervals, you can see how the data gets updated, and also you can see how like late data coming in at 12:04 actually affects the result table in the end, in the very latest trigger. So I've mentioned a lot of time concepts. I've talked about triggers. I've talked about watermarks. I've talked about window functions. So I just want to like give more examples on that real quick, how you deal with those. So if you want how to group data by time, you use the window function, you give it a timestamp column, and you give it some time amount. It says how you group data by time. This is the same in streaming and batch. Then by the watermark, you tell us how late data can be. It's given by the with watermark function. And triggers how often to emit updates. All right. So given all this background, let's talk about mapGroupsWithState. So mapGroupsWithState allows you to write your own arbitrary stateful processing algorithm, whatever you want to do. Basically, it supports per key timeouts in both event time and processing time, and it's currently supported in both Scala and Java. So it's not supported in Python yet. How it works is after you have your data set, you group by a key, and then you call mapGroupsWithState. You give it some timeout configuration. You don't necessarily have to have a timeout. You can say no timeout, and then you will always keep the state until you remove it yourself. And then you also give it a map function. So the mapping with state function will provide you the key, the grouping key that it's being called on, an iterator of values. So this is all the values that we've received for that key during that trigger. And then you will also have access to the state that gets that can be like updated across triggers. So in your mapping with state function, you can update or remove state, you can set your timeouts, or you can return mapped values. And like the map value you return could be anything. It could be, you could just be outputting the state as you update it, or you could be, for example, doing, like anomaly detection, and like your state would be, like a limit on, like how anomalous something is, and then you just output, abnormal values. So flatMapGroupsWithState applies the given function to each group of data while maintaining a user-defined per group state. It's invoked once per group in batch mode, so it doesn't actually, it's like similar to map groups in batch mode. It's invoked each trigger with the existence of data per group in streaming. So if you don't get values for a given group, and you don't, then your function doesn't run on that group. And it requires the user to provide an output mode for the function, and this defines how your function operates. So mapGroupsWithState is a special case of flatMapGroupsWithState where the output mode is update mode, and the output size is just one row per group. And also flatMapGroupsWithState also supports processing time and event time timeouts. So some use cases that you might have, you could do some alerting. You could monitor a stream using stateful logic with timeouts. I'm going to show examples of how to write within this flatMapGroupsWithState, but for example, you group by an ID, and then you do some function on your events, and then you write it out to PagerDuty. It's like creating alerts on PagerDuty. Or you could do sessionization. You could do like group by a session ID, and then you could use mapGroupsWithState here, where you always want to get the latest state of a session, and then you can just write it out somewhere as well. So just to show you how all these work, I want to do a demo on Databricks. Let me zoom in. All right, so what I have set up right here, I've set up my cluster such that all my logs are getting sent to Kafka. I've installed Kafka on my cluster. It's running. It's co-located with Spark. And what I'm going to do is I'm just going to do some real-time reporting and sessionization on it. So first of all, I just want to create like a topic on Kafka called sessions. And it's going to be a compacted topic, so it can behave like a key value store over time. I'm going to define 3 classes: an event, it has an action, it has a session ID, it has a given user, and it has a timestamp for that action. And then my user session, again, will track, like who's the user, is the session active, how many commands did this person run, how many notebooks did this person view, and what's the latest timestamp of the action. And here's just a convenience method. So my metrics is a streaming data frame. what it's doing is I'm just like ignoring all records that have null users and have null sessions. I'm just going to group by the session ID, and I'm just going to write a map groups with state and run this to see what happens. I'm outputting all the values to Kafka, my session's topic, in update mode. So inside this function, I'm not going to get too much into the details, but like if you want to do sessionization, you might want to have like an event time timeout where like the user just left your service or your browser or whatever, and then you want to like time that person out. If that person state has timed out, you just like remove the state and output the session as like is active false, for example. Here I just take a look at all the actions that the user did and then update my session metrics. If they logged out, I say like base state is active as false, and then I'm just running this stream right now. So if I look into Kafka, read this back from Kafka, we're going to see hopefully that I've run 1 or 2 commands in a couple seconds. Yes. Oh, Jules, what are you doing there?
Oh, sorry.
So yes, you can see me running 1 command here. And that's how update mode works. Basically, it'll get updated over time, all the actions. You can see as I run more commands, the active timestamps increase, and my sessions are updating in real time. So how does this change with append mode? So in append mode, what I want to do is I just want to output my result once the session is over. So it's the exact same code, except I just output an iterator of values when the session has, when the session is complete. So when my session is not active, I output it. If my session is active, I don't output it. But I also set a timeout timestamp of 2 hours, such that like if the user goes out for lunch, comes back and does stuff, I don't want that session to end. I want to see what they're doing. So if I run this code, now this stream is not going to actually output anything until the session is over. So Jules, if you could help me by logging out, we should hopefully be able to see Jules's log out here momentarily. All right. And we have our metrics of our aggregation states. We only have like 2 users active, and here you go. Jules logged out, and we got the result. And he only viewed 1 notebook in the meantime. All right, so sessionization's cool. What about stream joins? People love that. You can also achieve stream joins with flatMapGroupsWithState. The real, like nice APIs for joins on streaming data frames, that's going to be coming in Spark 2.3. But flatMapGroupsWithState is just such a powerful API that you can write basically any kind of stream joins that you want. You can define your left joins, left outer joins, right outer joins, inner joins, all that stuff just based in the logic of your flatMapGroupsWithState. So here what I'm doing is I'm sending all the logs from my cluster to Kafka, and I want to track how many error messages or log levels, like counts of the log levels I see per Spark version, just to track, are there bugs? So what I need to do here is basically define 2 data sets from 2 different streams, and define a catch-all schema, where you have both the left side of the join and the right side of the join as options in this union case class. And I also define the grouping key, for example, the instance ID of the cluster. So one stream I filter out basically where I'm going to get the cluster info and create my left side of the join. Another stream, I create my right side of the join. I also provide the grouping keys. And then I just union these 2 streams. And then in my join state, what I'm going to do is I'm going to keep track of the Spark version and some aggregated stats over time. So if I don't have the Spark version, what's going to happen is I'm just going to aggregate stats over time. You know, like info level has seen 5 messages, 10 messages, 12 messages. Warren has seen like 5 or 6 messages. And then once I have the Spark version, I don't need to keep track of that state anymore. I can just like output results as they come in. So as you can see here, I define all my classes. Just gonna put these in here with these guys. And I start my stream. So the way the join works is if the state has timed out, basically you don't output anything anymore. So you just remove the state because there's nothing to output anymore. If you're like doing window joins, you're grouped by windows, you don't need to keep track of that window anymore, so you clear some state. Otherwise, if the state exists, I want to get the old state. If not, I just want to create an empty state of it. And then once the rows come in, I just keep track of, did I see a Spark version? If so, update the Spark version. If I see a log message, I just get the log level and update my map accordingly, just increment the values in the map. And then if eventually I see an updated Spark version, I just, for each log level, I just output everything. If I don't see it, I just update the state until I get the new Spark versions. And as you can see, I'm starting to get joined values here, where I get info level for Spark 2.2 and Warren level, and there aren't many Warren level messages, so that's good, I guess. All right. So feel free to try all this out on Community Edition today. Spark 2.2 RC is released on Community Edition. It's free. Check it out. If you want more info on structured streaming, we've got a very long blog series at Databricks.com blogs. We've already released 4 blog posts around structured streaming. We've got more coming. You can follow us at Twitter at Databricks, and great blog posts coming up. So I urge you to check it out. And Spark Summit's coming up. Discount code Databricks. We'd love to see you there. Great things. Hackathon, Spark Hackathon. That's pretty cool. And shameless hiring post. That's my manager, Michael. We're only a 4-person team. Come help us out. We'd love the help. And you get to work on amazingly cool stuff. So thank you so much. And I can take your answers for my questions if you have any. And thank you.
You just prepared some answers to the questions. So if you have any questions, please. Anybody?
Okay, can you go to the third or fourth slide somewhere? I'm trying to kind of absorb still your update process.
Come on, man.
The third or fourth slide somewhere. The way you find the window and then see the one problem we have with Kafka consumer is that exactly one consumption problem. Now, writing your write ahead log,
Yes.
does that fix the problem or is still?
The way structured streaming has its Kafka source, it keeps tracks of all the offsets it's processed by itself. So it doesn't commit to Kafka, so there can't be any inconsistencies going along. So you will always get the exactly once processing from Kafka. When writing to Kafka, which Spark 2.2 also supports, I mean, it did until it has that transactional APIs, which they are adding right now, you still won't get the exactly once end-to-end because the Kafka is just not important yet as a sync. But the consumption side, you will get each record only once. And if your sync is idempotent, so we might reprocess some data, and if your sync is idempotent, that means you've already processed and outputted the data there, and we see that the data is there. Then we won't output it again. So we will just say, oh, we've already done this batch. The output is there, so just throw it away.
State, where you're in state.
Yes.
State, you have the state.
Yes.
State, you have the state, and you have write ahead law.
Yes.
So the two, they kind of.
They're always in sync. They're always in sync.
Any other question? I'll give a big hand to Burak. If you want to find out anything more about Databricks, there's a couple of guys here wearing Databricks t-shirt. Feel free to come and talk to us. Again, thank you all for coming. Give a big hand to Salesforce for sponsoring us and having fed us, and hope to see you again at Spark Summit. Cheers.